We are going to begin the content in our statics course. So we'll start with chapter 1, which is an introduction. So I'm going to go through the concepts in this chapter pretty carefully. The lecture should only take 1 day or at the most 2 days. But if you take a look on our Moodle page, what I would like to point out is that I've updated it a little bit, that the first homework assignment, which is a handout on unit conversions, will be due no later than Wednesday, August 28th. So that is actually next Wednesday. The unit conversion handout is right here. So we'll be talking about this a little bit later in the lecture, and we will work a couple of problems to get you started. But Chapter 1 itself in the textbook is the only chapter that has no homework associated with it. So there's no homework at the end of this chapter the way there will be in the future with future chapters, but we will work on this homework instead. All right, so to get started, I'm going to go over to the document cam. And we're going to just talk a little bit about what is going on in statics. Okay, so last time when we talked, we said that statics is the first of 3 courses that is about engineering mechanics. And there are more courses as well, but in a typical 2-year sequence of engineering science courses. It's the first of 3 courses in engineering mechanics. And so the first question then would be, what is mechanics, or what is engineering mechanics? Well, the answer to that is, it is the science that describes and predicts the condition of rest or motion of bodies acting under forces. And those bodies can be, so we have rest or motion, and we have particles, rigid bodies, deformable bodies, and sort of the ultimate deformable substance, fluids. So I guess that's really 4 courses. But statics, we talk about particles and rigid bodies at rest. So in other words, if we do have any motion, the motion is non-accelerated. So that means we could have a constant velocity, but in general, statics talks about things where the velocity is equal to 0. So we're talking about things that sit still. Now, when we talk about particles, we're just talking about things where the shape is not a particular consideration, where the mass can be considered a point mass. And rigid bodies means that when we put forces on the bodies don't deform or break or bend in any way in response to that. So we assume that whatever loads we put on the body can deal with without deforming or breaking. Later on in other courses, we'll talk about bodies that actually deform or break, and then, of course, fluids that only bear certain types of loads. So anyway, when we continue with this idea, we have some fundamental concepts that we need to discuss. And those of you that have had physics at some point, some of these terms may be familiar to you. If they're not familiar to you, that's fine. You're in the right place. That's why we're going through it right from the beginning. But it can be a little confusing because sometimes the terms that are used in a particular way in a science course are used in a general way that is not 100% accurate in everyday life. So we're going to talk about these ideas from a point of view of science. We're going to talk about them in a precise way, right? So we can talk about space, we can talk about time, we can talk about mass, which I would like to start by saying mass is not equal to weight, and I will define that for you very soon. And we also talk about force. Okay, so these are sort of like the fundamental concepts beside particles and rigid bodies. Okay, so these are like the big things that we're going to be talking about here in statics. Space is associated with a position, and we can define the position of a point by providing 3 lengths of measures from certain reference points or the origin. Most commonly, or initially, we will talk about rectilinear space, which is defined by Cartesian coordinates. In other words, XY, fixed reference frame, sometimes a Z coordinate, but we will discuss this all at length as we proceed forward. So to define an event, not only is the space necessary or the position, but we also need to define when. So space answers the where, and time answers the when. So we also talk about not just absolute times, but intervals of time. So if something happens between 2 p.m. and 3 p.m., we're still talking about time, but we're talking about an interval of 1 hour. Now, when we talk about mass, and as I say here, it does not equal to weight, mass is fixed, and weight is relative to a gravitational field. So the easiest way to think about this is if you are an astronaut, for example, this is you. You're an astronaut, and when you are on Earth, you weigh, let's say, 150 pounds. When you go in your little spaceship and you go to the moon has 1/6 of the gravity of the Earth, relatively, more or less. And so when you go to the moon, your size is still the same. The amount of you has remained unchanged. So your mass is still the same. Let's say mass equals mass. Mass equals mass. Okay? But you weigh less. That's why astronauts, when somebody's in a lower gravitational field, they can jump around much easier. So for example, their weight would be 1/6, more or less, of the 150 pounds. And so if you take 150 and you divide it by 6, that is 25 pounds. All right, so you're much, much lighter on the moon because you are less attracted to the moon than you are to the Earth, but your mass remains the same. In other words, you didn't shrink. You're not 1/6 the size. There's not 1/6 as many atoms in your body. You have the same number of atoms, you have the same number of molecules, you're the same size. You've just, something else has changed, and that changes the relationship between you and the planet or satellite that you are on at that particular time. Now, a little bit later in the lecture, we're going to talk about this quite a bit to get that distinction. It's also one of these things that's made difficult in everyday life because in the metric system, which is called the System International of Units, or International System of Units, mass is measured in kilograms, but weight is measured units of force, which are called newtons, which are less familiar to us. And in the system we use, it's not really a system, but the way that we measure things in the United States, which has a lot of different names, but I like to call it the U.S. Customary System, the weight is what we talk about more. It's measured in pounds. But mass is measured in a unit called a slug. And I'll break this all up for you mathematically so that you have an example of this in your notes. But we more routinely use kilograms or measure of mass in the SI system. We more routinely use pounds or measure of weight in the U.S. Customary System. So in other words, The astronaut's weight in pounds is different, but the astronaut's mass in kilograms or slugs remains the same. All right. So we just talked about the force of gravity or gravitational attraction, and talking about the idea of force in general is the action of one body on another. So this is an example of what I would call a free body diagram, which you'll be drawing a lot of in this class and in all of your mechanics classes. A free body diagram, if I have a ball resting on the surface of a table, for example, it pushes down on the table. Here's my table legs. But that also means that the table, if the ball is stationary, the table pushes back on the ball. And if the ball weighs and is stationary and the ball weighs 10 pounds, that means that the table pushes back with a weight of 10 pounds. It also means that if this table is resting on the floor, that the legs of the table push down on the floor in a distributed fashion, which we'll talk about on a different day, but that the net effect is that the floor has to push back on the table with that same amount of force. If none of those things happen, something is going to break, and that's not what happens in statics class. Everything sits still. We'll talk about breaking later. But, for example, if the ball was too heavy to sit on the table might bend. And then if it became extremely much too heavy, if the table is made out of paper, for example, perhaps it would fall all the way to the floor, and then the force would be borne by the floor. Or perhaps if the surface of the table was very brittle, it would break, and once again, the ball would fall to the floor, and then the floor would have to push back directly on the ball. But that's kind of the way that forces work for stationary things. Now, the governing law for this is called Newton's second law of motion, which says that force is equal to mass times acceleration. And if it is not moving, if the velocity of things are equal to 0, then the acceleration is also equal to 0. In the general sense, the instantaneous. And so if this is equal to 0, this says that the forces are equal to 0. Well, that looks quite uninteresting, but basically when there's more than one force in more than one direction, this little arrow means it's a vector, which I'll talk about a little bit later, not today, but later on. So we have to take forces in all sorts of directions and sum them to 0. Now, what that means, for example, is this ball pushing down on the table, that all happens in the up and down direction or the y direction. This is not offset in any way by me pushing on the table in the x direction. If I push on the table in the x direction, the table is going to move this way unless it's opposed by something, say a wall, that gets in the way of the x directional force. So, in other words, summation vector forces equals 0, not just arithmetic forces summed to 0. Now, it's always important to note at this point that somebody will say, well, you know, Einstein's relativity, not necessarily true, time, space, blah, blah, blah. And the answer is that is absolutely true, but when we're talking about statics, when we're talking about tables and balls and trains and automobiles, relativistic effects are not factored in because they are not of a large enough magnitude. If you start moving things close to the speed of light, then you do get this idea. But at this stage of the game, we don't have to consider it at all. All right, so this is Newton's second law. Might lead you to think, what is Newton's first law? Well, the first law is that if the resultant force acting on a particle is 0, the particle remains at rest if it was originally at rest, or moves in a constant speed with a straight line if it was originally in motion. So this really looks like this. I guess I should draw this one down here. And this really looks like this, where A could be anything. The second law says if a resultant force acting on a particle is not 0, the particle has an acceleration that is proportional to the magnitude of the resultant in the direction of the force. All right, and then the third law, Newton's third law of motion, talks about gravitation. And basically, this gives us a relationship between force or weight and mass. So it looks like this, and I will describe each of these terms. But basically, it says that the force of attraction between two particles or two bodies, one of large mass m and one of small mass little m, is proportional to the product of those two divided by the distance. R is the distance between the two bodies, or the centers of mass of the two bodies, raised to the second power, times the universal gravitational constant. Now, this is not little g, which we've talked about in other classes probably, where we know that little g is 9.8 roughly meters per second squared, or 32.2 feet per second squared. Little g and big G are not the same quantity. G is a number that, oh, and this is on Earth, by the way. So on the moon, for example, it would be 1/6 of this. Big G is universal. It's the same everywhere. It has different units, and it's a different value. But in this case, we could relate these two to each other by saying, for example, if you're standing on the Earth, here you are again. Okay. The center of the Earth is down here, so the distance between you and the center of the Earth is r. The mass of the Earth is big M in the equation. The mass of you is little m in the equation. And the force here would be equal to your weight on Earth. And G has a value that is actually given in your textbook. I don't have it right in front of me, but I will let you know what that is before the end of the day. Now, the other thing I'll go ahead and do this. Let me come over here to the podium PC and get you that number. So the universal, capital G, is called the universal constant, okay? And if you see what it is, it has different units. For example, it's 6.6 with some change times 10 to the negative 11th Newton meter squared per kilogram squared. Now that is in the SI or metric system. And this is a different one. If we look at the value of G in US units, let's see if we can find some more units of this. There we go. In SI units, this is the wrong G. Sorry. See how it's the little g? We need to get the capital G. And we're still not going to find it. So this is a confusion that we need to make sure we don't fall into. The universal gravitation constant. Okay. So we have it here in Newton meter squared per kilogram squared. I would love to find that in units in the English system, but we can convert that. We can just go ahead and do that. As a matter of fact, that would be a nice little exercise, so let's go ahead and do that. All right, so here I am told that the gravitational constant, capital G, has a value of 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. Okay. If you take a look at the document cam, this is just the value that I pulled off of universetoday.com. Now, in the English or U.S. Customary System of units, we can break apart all of these units and think about the dimension that they measure. So in other words, a Newton measures the dimension of force, which is measured in units of pounds. Meter measures the dimension of length, which is measured in feet, and kilogram measures mass, which is measured as slugs in the U.S. Customary System. So if we found conversions between these quantities, we could then write G in U.S. customary units as well. So what I'm going to do is just go back. I'm going to go ahead and work that problem. So let's say newtons or pounds per newton. It doesn't matter which way, per newton. Okay. So the answer is 1 Newton is equal to 0.2248 pounds. And I'm just writing these down. I will flash over to that after we're done with this. Meters to feet, meters per foot. You may be more familiar with some of these than others, but 1 foot is equal to 0.3048 meters, and last, kilograms per slug, or slugs per kilogram. Slug per kilogram. Okay, so let's take a look at that. 1 kilogram equals 0.0685 and some change slugs. Okay, so if we come back over here, we can do something called unit conversion or factor label method to change the units. And the way that we do that is we look at each one of these units separately and convert it based on these numbers. If the unit is squared, we have to square the conversion factor as well. But since 1 Newton and 0.2248 pounds represent the same quantity, if I put 1 Newton over 0.2248 pounds, that's 1. The value is 1. So I can multiply by that. I could also multiply by 0.2248 pounds divided by 1 Newton. So in other words, to convert, first of all, to start with newtons, start with this number, 6.673 times 10 to the negative 11th Newton. So then I know that I have 1 Newton. The Newton is in the top, in the numerator, so I put the Newton in the denominator, 0.2248 pounds. And this is my unit conversion that has a value of 1. Then I have a meter squared, and I wish to convert meter squared is in the numerator, so I wish to put meter squared in the bottom. Now since I'm squaring the meter, I have to square the value as well, 0.3048. So that's quantity squared, 0.3048 meters squared per 1 foot squared. 1 squared is just 1. So this is an effective unit conversion. And then I have kilograms in the denominator. I should have written out this entire unit is what I'm thinking. Newton meter squared per kilogram squared. There we go. Just for clarity, so I have kilograms squared in the denominator. That means that here I want to put 1 kilogram. I want to square that. 1 squared is 1, so that's good. But in the bottom, I'm going to have the quantity 0.0685 slugs squared. Okay? So if I take this number, multiply it by this, divide by this squared, divide by this squared, what happens to my units? Newtons go away. Meters squared goes away. And kilogram in the denominator goes against kilogram in the top. So the value that I would get for G would be, I don't know if you can see my calculator, there you go, 6.673. I'm just going to carry that, that didn't go right, 6.673 times 0.2248, and then I divide that by 0.3048 squared, and I divide again by 0.0685 squared, and that number is 3441, and I still have that times 10 to the negative 11th, but now my units have canceled out So I'm left with pounds, feet squared per slug squared. Okay, now it's not proper to write this. In other words, this is times 10 to the minus 11th, and this number itself is 3.441 times 10 to the third. So if I take 3.441 times 10 to the third times 10 to the minus 11th, this becomes 3.441. Add those two exponents, and I get times 10 to the minus 8 pound foot squared per slug squared. Okay? So that actually serves two purposes. We talk about the gravitational constant, the universal gravitational constant, and we also talk about doing unit conversions with the factor label method. So I'm going to do a few more of these because this is going to be your homework for tonight. But there are a few things to talk about first. One is we have two systems of units that we have to be conversant with. One is called the SI, or metric system, which is a system, truly a system, scientific and consistent. And then we have what it is we use in the United States, which I refer to as the U.S. Customary. It's also sometimes referred to as SAE, or British Engineering, or Imperial. It has a bunch of different names, and it's not really a system at all. I like the name U.S. Customary because it indicates that the reason we use it is because we are accustomed to it. But the United States trades with almost every country in the world, and so since we use this system, everybody needs to use this system. Now, the other part about this is that almost every country in the world uses the SI system. Last time I checked, there were only 3 countries that did not use the SI system. One was Myanmar, which is a country in Southeast Asia that's an exporter of teak wood. The other is Liberia in Western Africa. And I think Liberia has actually adopted the system since I last checked. But Burma, or Myanmar, is an exporter of teak wood, and they have a different way of measuring the wood that they export. But in the U.S., we just export and import everything, so everybody really needs to be conversant with this. But having said that, the SI system, or metric system, is very logical. This is just a page from your textbook, page 7, and you'll see that we have prefixes. They're a combination of prefixes and units, base units or secondary units. So 10 to the 12th always is said as tera, and always uses the symbol T, and it always represents the same amount, 10 to the 12th. So you could have a terabyte, which is 10 to the 12th bytes, or you could have a terameter, which is 10 to the 12th meter, or you could have a teragram, which would be 10 to the 12th gram. So larger to smaller, we go all the way down to the one that you're probably more familiar with would be a nano, which is 10 to the negative 9th. So you could have a nanometer, a nanobyte, which would be almost nothing, or a nanometer. So you always use the same system of prefixes with the same base units. Okay. In the SI system, this is also in your textbook, the basic quantities that we measure are measured in these particular units, and the symbols are given. So, for example, when you talk about acceleration in meters per second, it's little m, or minuscule m divided by minuscule s raised to the second power, and so forth. We will not use all of these in this class, but this is just a good summary. It's much more random, I guess I would say, in the U.S. customary system, because once again, it's just something that we are used to. Now, we also have in your textbook a table, 1.3, that shows those same quantities and what their units are or can be in the U.S. customary system and the equivalents in the SI system. But the important thing to remember is you can always use this data. I'm not going to make you memorize anything, but you need to use it appropriately, and you need to be able to convert between one set of units and another pretty flawlessly. And that's actually what your first homework is going to involve. So I want you to work through this unit conversion handout that is on your Moodle page. So I'm going to take a look at a couple of the problems, if the computer will actually keep this up. Ask me later. Okay, so there are some of these units that are relatively simple, where they ask you, for example, to put kilometers into miles, number 4. And I want to also point out that these numbers are not 100% consistent because I took them from different sources, and I really felt that only doing 5 or 6 problems was sufficient rather than doing 30 or 40 problems. So I wanted to get more different kinds of problems instead. But I'm going to do number 4 for you, which is 450 kilometers equals how many miles? Okay, so if we go back to the document cam and we look at that problem, what we need to do is to decide then how many kilometers are there in 1 mile. Okay, so you can get that information all the time out of your textbook, or you can get it online. And so I'm just going to type in kilometers per mile. I'll tell you that 3.2 miles is about the same as 5 kilometers, but the actual conversion factor is 1 mile equals 1.60934 kilometers. So the way that I do this problem is I take the 450 kilometers and then I multiply it by a unit conversion factor, either this over this or this over this, because the equivalent, since they're the same quantity, that's equal to 1, and you can multiply 1 by anything and get the same number. But I have kilometer in the numerator here. I want to cancel kilometer, so I put kilometer in the denominator here, and I put mile in top. Okay? So then what happens is kilometers cancel out. My answer will be in miles, and I can see then that what I have to do is take 450 and divide it by 1.609 and some change, and that answer is 279.67. Now, this is a good time to talk about significant figures. In this class, we just have to get close. It doesn't have to be exact. But 450, the way it's written, without a decimal point, has 2 significant figures. Every conversion factor is considered exact. So your answer is going to depend on the data input, not the conversion input. So that means that this answer should be written with 2 significant figures. 279.67 written with 2 significant figures. Looks like that, 280 miles with no decimal point. Now, if you had written this 1 or 2, 1 off, it's fine, but I really don't want it to be 279.6742986 or whatever your calculator tells you. I prefer it to be exactly the same, but if you carry out 1 extra decimal place, that's fine, but please get in the ballpark. And if you have any questions about sig figs or sig digits, please let me know. All right, going back to the handout. Let's take a look at another problem. A little bit more complicated. All of these, I think you can work through. Now, this talks about conversion on temperature, and the formulas are given. Centigrade or Celsius is the system that is used in the metric system. And once again, it's based on that whole kind of powers of 10 idea, where water boils at atmospheric pressure at a temperature of 100 degrees centigrade or Celsius. Water freezes at atmospheric pressure at a temperature of 0 degrees Celsius. So Fahrenheit, which is the system that we use in the United States, is a little bit different. It was based on some salted solutions that a scientist was working with. So it actually turns out that water boils at 1 atmosphere pressure at 100 degrees centigrade or 212 degrees Fahrenheit, and it freezes at 1 atmosphere of pressure at 0 degrees Celsius or 32 degrees Fahrenheit. So these two are equivalent, and putting them together, you can develop a scale. They're also linear. The scales are linear. So that means that you can convert, if you have a Fahrenheit reading on a temperature, you first subtract 32, then you, with that difference, you multiply it by 5/9, and that will give you the degrees centigrade. For Fahrenheit, it's a little different. You do the multiplication first, and it's the reciprocal, of course, but you take centigrade or Celsius temperature, multiply that number by 9/5, and then take that product and add 32. So if you were to go from one of the problems in your problem number 19 is 40 degrees centigrade equals how many degrees Fahrenheit? And then I'll do one the other way, 68 degrees Fahrenheit equals how many degrees Celsius or centigrade? Okay, so to go this way, I want to use this formula because I want to come out in Fahrenheit. So I would say the degrees Fahrenheit here equals 40 times 9/5, and then I add 32. So if I take 40 and multiply it by 9/5, 5 goes into that 8 times. So my Fahrenheit degrees would be 9 times 8, which is 72. So this is 104 degrees Fahrenheit. Okay, so in other words, I do the multiplication first, then I add. Over here, it's a little bit different. I put Fahrenheit in and I subtract 32 first. So 68, the first thing I would do is subtract 32, and that gives me 36 degrees Fahrenheit. Then I multiply that number by 5/9. 9 times 4 is 36, so that turns out to be 20 degrees centigrade. Right? And then, just as a point of interest, the scales look kind of like this. If you think about it, there's going to be a place where they cross. If this is 0 degrees and we have Fahrenheit and Celsius, they actually cross at negative 40 degrees centigrade. So or negative 40 degrees. Negative 40 degrees centigrade is exactly the same temperature as negative 40 degrees Fahrenheit. And you can check that out with these two formulas. But I always make a little joke at that point, and I say it's because negative 40 is just really cold. It does not matter how you measure it, whether you use Fahrenheit or Celsius. They're both just cold, cold, cold. So there you go. Now, the only other thing I want to show you about this handout, the only other type of problem, I think you're going to be able to handle the rest of these quite nicely. But when we talk about rates, areas, and volumes, these are the last problems. And once again, they're not in numeric order. But basically, if you have a unit that is cubed or squared, you need to cube or square the conversion piece as well. And if you have rates, just like I showed you with the universal gravitational constant, you need to take care of each set of units by itself. That's the easiest way to do it. You can do it in shortcut ways, but while we're getting used to this, this makes a lot more sense. So the first thing I'm going to do, for example, is to convert, and there's some weird ones in here as well, like liters to meters cubed. A liter is a measure of volume already. It's 0.1 meters cubed, but you can take a look at that and see what it is. But so anyway, this one is already cubed. There are some other units like that, like acres are already squared. There's no such thing as square acres. Acres are already squares. But anyway, having said that, I've also got some other ways that they write these things in the U.S. Customary System. In other words, square inches is sometimes written instead of inches raised to the second power. So just so that you'll be aware of that. All right, so the one I want to do for you is number 6, which is 27 meters squared, and I want to convert that into feet squared. Okay. So basically, what do I know? I found this out before, is that 1 foot is equal to 0.3048 meters. I'm just going to check my numbers. And so my conversion factor is 1 foot equals 0.3048 meters. Okay, so if I start with meters, I have 27 meters squared. I have meters in the numerator here, so I need to put it in the denominator here. It's per 1 foot. But since this is squared, I need to square that entire quantity and square that entire quantity. Well, the good news is that 1 squared is just 1. But 0.3048 squared is a different number. So I get 27, and I divide that by 0.3048 squared, and that number turns out to be 290.6255 meters squared. Cancels meter squared, so I'm left with foot squared. Okay, I'm not quite done yet, am I? This has 2 significant digits. I don't rely on the significant digits of my conversion factor. So I need to write this answer with 2 significant digits, which means then that I would write it as 290 feet squared. 2 sig figs, 2 sig figs. There's your answer. All right, ladies and gentlemen, well, that's it for our first lecture. This is a lot of material. On Monday, what I'd like to do for our next class is to do a problem-solving session. So I'd like you to bring that handout with you, and I would like you to bring any questions that you have about Newton's first, second, or third laws and the universal gravitational constant, and we can work those out in class. But we have finished, essentially, we have finished Chapter 1. There's just one more little thing that I'll talk to you for a moment about numerical accuracy, and we'll begin on Chapter 2 on Wednesday, which is also when this handout is due, the work on the handout is due, submitted through Moodle. So thank you for your time, and I will look forward to seeing you next time.